Imagine this. Buried deep in the heart of our Milky Way, just 26,000 light-years away, lurks an invisible monster with the crushing weight of 4 million suns, warping space itself and devouring anything that dares get too close. What if I told you we've not only found it, but snapped its picture, revealing secrets that could rewrite everything we know about our cosmic home? Stick around as we uncover the wild story of Sagittarius A star, the quiet beast at the galaxy's core. If this hooks you, smash that like button, subscribe for more mind-blowing space dives, and let's blast off right now. Prepare yourselves. We begin. Deep in the swirling chaos of our Milky Way, where billions of stars huddle together like a cosmic crowd at a midnight party, there's a region so dense and dusty that it has mocked humanity's gaze for centuries, hiding the true heart of our galaxy behind a veil thicker than any fog on Earth. Picture this. From our little perch on a pale blue dot, we stare up at the night sky and see that faint, milky band stretching across the heavens, a glow that's not mist or cloud, but the blended light of countless stars packed so tightly they blur into one another. And right in the thickest part, toward the constellation Sagittarius, everything just stops. Light scatters, shadows swallow details, and what should be the bustling core of our home galaxy looks like a smeared mess of confusion. For thousands of years, ancient stargazers, from Babylonian priests to Greek philosophers, spun tales of gods and heroes in those stars. But they never suspected the real drama unfolding behind the curtain, a barrier built not of stone or silk, but of interstellar dust, those tiny specks of carbon, ice, and rock drifting between stars like forgotten confetti from the universe's creation party. These particles, each smaller than a grain of sand, spread out over vast distances, absorb and scatter the visible light our eyes and early telescopes crave, turning the galactic center into a blacked-out zone where stars closer to us shine bright, but anything deeper vanishes into oblivion. Early astronomers, armed with nothing but brass instruments and star charts, mapped the skies with painstaking care, counting twinkles in every direction to guess the Milky Way's shape. But when they pointed towards Sagittarius, they hit that wall of obscurity, assuming the galaxy was just a loose swarm with no sharp middle, perhaps even placing our sun near the center because stars seemed evenly scattered all around. A classic case of missing the forest for the dust-choked trees. William Herschel, that 18th century trailblazer with his homemade telescopes, spent nights tallying stars like a cosmic accountant, concluding the galaxy resembled an elongated grindstone with a smack in the middle. But his counts faltered in the bulge's direction, where dust devoured half the light, leaving gaps he couldn't explain, gaps that whispered of something grander yet unseen. Fast forward to the 19th century, and the plot thickened as better lenses revealed dark lanes cutting through the Milky Way's glow, those infamous rifts that turned out to be dust clouds gobbling up starlight, not empty voids, but highways of obscurity, blocking the view to the core, where hundreds of billions of stars cram into a swollen spherical bulge, denser than the galaxy's outer arms by orders of magnitude. This bulge isn't flat like a pancake. It's puffed up and round, a stellar pressure cooker, where orbits whip around faster, collisions spark more drama, and gravity pulls everything inward toward an invisible anchor we couldn't yet name. Imagine trying to peer through a blizzard of glowing embers. That's the galactic bulge for visible light observers. Stars overlapping in a frenzy, their lights bleeding into one another, while dust lanes streak like cosmic graffiti, rendering the center a puzzle wrapped in an enigma. By the early 20th century, the frustration mounted as spectroscopes and photographic plates promised clarity, but delivered only tease, showing the bulge as a hazy swell in maps, hinting at immense density, yet refusing to part the veil, leaving scientists to debate if the galaxy even had a true center, or if it was just a haphazard blob of light. Some posited a central cluster of stars, brighter than the rest. Others imagined a void, but no one could prove it. Trapped by the very stuff that birthed those stars, interstellar medium, that brew of gas and grains, recycling elements from dead suns into new ones, now playing gatekeeper to the galaxy's secrets. The breakthrough simmered on the horizon, but it took a shift in perspective to crack the code, realizing that visible light was the wrong tool for this job, too easily snuffed out by the dust's greedy grasp. Enter the radio waves, those long, low-frequency whispers that slip through dust like ghosts through walls, carrying tales from depths where optics failed. And in the 1930s, an unlikely hero stumbled upon the first crack in the armor. Karl Jansky, a young engineer tinkering with phone lines at Bell Labs, wasn't chasing stars. He was hunting static that garbled transatlantic calls, building a rotating antenna array that looked like a merry-go-round for the skies, spinning it slowly to pinpoint noise sources at around 20 megahertz. Months of data revealed patterns, thunderstorms nearby, lightning afar, but one persistent hiss peaked every 23 hours and 56 minutes, syncing not with the sun, but with Earth's spin toward the stars, pinpointing a source in Sagittarius, right at the galaxy's heart. Jansky's 1933 paper dropped like a quiet bomb in astronomy circles, birthing radio astronomy from an engineering side quest. Yet it took years for the field to catch fire. His antenna dismantled as war loomed and priorities shifted. But the seed was planted, and by the 1940s, amateurs and pros alike tuned in, with Grote Reber erecting a backyard dish in Illinois to map the radio sky, confirming Jansky's signal as a blazing beacon from the Milky Way's core, dubbing it Sagittarius A after the constellation's first radio source. World War II accelerated tech, radar wizards, turning wartime gizmos into post-war telescopes, arrays sprouting across deserts and mountains to chase those elusive waves, revealing a sky alive with emissions from nebulae, supernovas, and now piercing the dust to sketch the galaxy's true form. By the 1950s, the galactic bulge emerged not as a blank slate, but a riot of activity, radio maps outlining spiral arms coiling around a dense center, stars and gas clouds lighting up in wavelengths that laughed at dust's blockade. Yet Sagittarius A stood out, not a diffuse glow but a compact hotspot, steady and strong, hinting at something extraordinary crammed into a tiny space, far from the sprawling clouds elsewhere. Astronomers puzzled over it. Was it a star cluster, a supernova remnant, or something wilder? The dust still cloaked visible details, but radio eyes widened the view, showing the bulge as a stellar metropolis, old giants and young clusters mingling in gravitational tango, all orbiting that enigmatic point. Decades of refinement followed, baselines stretching longer for sharper images, interferometers linking dishes to mimic massive apertures, and by the 1970s, the veil thinned further as infrared joined the party. But that's a tale for later whispers. For now, the hidden heart pulsed with mystery, its dust fortress guarding a force that shaped orbits across 26,000 light-years, pulling the galaxy into cohesion while evading our sight, a silent sentinel in the stellar throng. Early maps faltered, but each failure fueled curiosity, from Herschel's grindstone to radio's revelation, proving the center wasn't empty, but brimming, a bulge of 400 billion stars or more, densities soaring 1,000 times over the disk's edges, dust particles forged in stellar furnaces, recycled carbon from ancient explosions, now blocking our quest, yet their very presence testified to the galaxy's vitality, birthing worlds and wonders alike. Jansky's hiss evolved into a symphony. Instruments like the Green Bank Telescope in West Virginia or Jodrell Bank in England, capturing finer details, showing Sagittarius A as three parts, a western arc, an eastern extension, and a central spark that refused to blur. This complexity baffled, suggesting ionized gas, young stars, or exotic engines. But the compact core, later christened Sagittarius A, Star screamed anomaly, its radio output steady yet variable, flickering like a watchful eye. The bulge's chaos amplified the challenge. Stars zipping at hundreds of kilometers per second, gas clouds colliding, all while dust absorbed 80% of incoming light, scattering blues more than reds, tinting the little we saw crimson. Pioneers like Jan Oort in the Netherlands theorized a central condensation from velocity fields, gas streaming inward, but proof eluded until tech caught up. By the 1960s, the 100-meter Effelsberg dish in Germany and Arecibo's giant ear in Puerto Rico tuned deeper, resolving Sagittarius A to arc minutes, small as a pinprick from afar, yet screaming power equivalent to 1 trillion suns if visible. The hidden heart wasn't just obscured, it was alive, magnetic fields twisting plasma into radio bursts, hinting at forces beyond stars, perhaps a beast stirring in the depths. Astronomers debated endlessly. Was it a dense starball, a collapsed cluster, or the long-sought galactic nucleus? Dust's tyranny reigned, but cracks appeared as balloon-borne detectors glimpsed infrared leaks, arm glows from heated grains, betraying inner heat. Still, the core stayed coy, its mass inferred from motions. Stars tugged off course by unseen hands. The 1930s whisper grew to a roar, Jansky's static, unveiling a universe where dust was no barrier, but a lens for new sight, transforming the bulge from myth to measurable marvel. Centuries of squinting yielded to listening, the hidden heart beating in radio rhythms, promising revelations that would shake foundations. For what lay buried there wasn't mere stars, but the architect of our galactic dance. What if the crackle on your old radio phone call wasn't just weather playing tricks, but the first whisper from the stars themselves, a cosmic murmur slipping through the dust that had blinded us to our galaxy's deepest secrets for ages? Picture a young engineer named Karl Jansky in the early 1930s, not chasing dreams of the universe, but wrestling with everyday annoyances at Bell Telephone Labs in New Jersey, tasked with silencing the static that garbled transatlantic chats, those faint hisses and pops that frustrated callers from New York to London. And to hunt them down, he crafted a clever setup on a quiet plot of land, an antenna array spanning over 100 feet, mounted on wheels scavenged from Model T cars, spinning slowly like a merry-go-round under the open sky to sweep the heavens for culprits. Jansky spent months logging data at frequencies around 20 megahertz, wavelengths long enough to dodge buildings and trees, but sensitive to whatever stirred the airwaves, first pinning down nearby thunderstorms as sharp bursts that rattled the receiver, then distant lightning storms reflected off the ionosphere as steadier drones. But lingering in the background was a third noise, a faint, steady hiss that rose and fell, not with earthly rhythms, but something stranger, peaking every 23 hours and 56 minutes, a sidereal day that synced with the stars' slow parade rather than the sun's daily loop. At first he wondered if the sun was the source, tracking its arc from east to south to west, but as weeks turned to months, the hiss shifted ahead by 4 minutes each day, defying solar patterns and pointing instead to fixed points beyond our world, a puzzle that gnawed at him through cold nights and foggy dawns, until chatting with a colleague, astrophysicist Albert Skellett, sparked the realization this was no terrestrial tantrum but a signal from deep space, the first extraterrestrial radio waves ever caught by human hands. By September of 1932, Jansky zeroed in on the direction, aligning his spinning antenna with star charts to find the hiss strongest toward the constellation Sagittarius, that archer's bow in the summer sky, a region already suspected by optical astronomers like Harlow Shapley as the Milky Way's true core, some 26,000 light-years distant, hidden behind the impenetrable fog of interstellar dust that scattered visible light like fog scatters headlights. He announced his find in April of 1933 at a Washington meeting of the International Scientific Radio Union, His paper titled Electrical Disturbances, apparently of extraterrestrial origin, hitting the proceedings of the Institute of Radio Engineers later that year, even making front-page news in the New York Times, and earning him a spot on NBC to explain star noise to a baffled public. Yet the astronomy world barely blinked, too wedded to glass lenses and starlight to grasp radio's potential, while Bell Labs, pinching pennies in the Great Depression, shelved the project as irrelevant to phone lines, leaving Jansky to tinker on telephones until his early death in 1950 at just 44. His merry-go-round dismantled and forgotten in a field, but seeds don't die easily, and across the Atlantic, word trickled to hobbyists and engineers, hungry for the next frontier, none more eager than Grote Reber, a Chicago radio whiz and amateur stargazer who devoured Jansky's paper in 1933 and vowed to build bigger, poring over blueprints in his spare time to erect the world's first true radio telescope in his Wheaton backyard by 1937, a 31-foot parabolic dish of galvanized sheet metal on a tilting frame, handcrafted from scavenged parts and aimed at the skies with homemade receivers, tuned to 90 megahertz at first, then dropping to 16 megahertz when higher bands proved too noisy from city lights and power lines. Reber's nights became a vigil, the dish creaking under moonlit rotations as he mapped radio intensities across the heavens, confirming Jansky's Sagittarius signal as a blazing hotspot amid a fainter band tracing the Milky Way's plane. His 1940 map, the first radio sky survey, showing emissions strongest at the center and fading outward, proof that our galaxy glowed, not just in visible light, but in these invisible waves, slipping past dust clouds that optical scopes could only curse. World War II turbocharged the tech, radar engineers honing antennas for battles over Europe and the Pacific, skills that post-war poured into astronomy as surplus gear flooded labs, birthing arrays like the one at Jodrell Bank in England, where Bernard Lovell, in 1946, detected meteors streaking radio trails, or the Naval Research Lab's dish in Washington, scanning for Soviet signals, but stumbling on cosmic echoes instead. By the late 1940s, radio astronomy exploded into a full-fledged field, with Jansky's hiss evolving into detailed portraits of the galaxy's arms, those spiral swirls of gas and stars, coiling around the core like a pinwheel in flames, and Sagittarius A, emerging not as a vague blur, but a complex trio of sources, the brightest a compact point, screaming anomaly, its radio output steady yet flickering subtly, hinting at a powerhouse far beyond normal stars. These waves, born from electrons, spiraling in magnetic fields, or atoms colliding in nebulae, carried tales dust had buried, revealing the bulge's frenzy, hundreds of billions of stars crammed into a space smaller than the galaxy's outer reaches, orbits whipping at thousands of kilometers per second, gas clouds birthing new suns, while old ones exploded in supernovas, all orbiting that enigmatic heart. Interferometry joined the party in the 1950s, linking distant antennas to act as one giant eye, baselines stretching miles for sharper views, like the Owens Valley setup in California, resolving sources to arc minutes, or Australia's Parkes dish in 1961, tuning into hydrogen's 21-centimeter line, that subtle shift when atoms flip spin states, mapping neutral gas flows toward the center and clocking rotation speeds that screamed massive unseen mass. Sagittarius A, sharpened in these nets, its central spark, later dubbed Sagittarius A star, shrinking to under 10 arc-seconds by 1955, with the Ratcliffe and Pawsey arrays in Cambridge and Sydney, no longer a broad glow but a pinpoint, suggesting something tiny yet ferocious, perhaps a dense star cluster or ionized plasma fountain. But its variability, flaring 20% brighter some days, whispered of deeper drama, magnetic storms or in falling matter, fueling bursts. The 1960s brought global networks, very long baseline interferometry, linking continents via atomic clocks, syncing data, the first transatlantic hookups in 1967 between Westford in Massachusetts and Craig in Ontario, peering at Sagittarius A with millisecond Ts, though full resolution waited decades. Meanwhile, continental drifts in Europe and America built behemoths like the 100-meter Effelsberg in Germany or Green Bank's 300-foot Ear in West Virginia, both feasting on the core's emissions at centimeter wavelengths, where dust thinned and details bloomed. These radio eyes unveiled the bulge's layered chaos. Molecular clouds, towering light years high, masers, microwave lasers from water vapor, pinpointing young stellar nurseries, and supernova remnants like the one near Sagittarius A, East, radio shells from exploded giants echoing across the bulge, but the central source stole the show, its spectrum peaking at centimeter bands, synchrotron radiation from relativistic electrons, tracing tangled fields, implying energies rivaling quasars, yet confined to our quiet galaxy. Astronomers like Jan Oort in Leiden used velocity dispersions, gaze blue-shifted approaching and red-shifted receding, to infer a central engine pulling with 4 million solar masses, though proof lingered. Radio maps by 1965 with the Westerbork Array in the Netherlands, outlining the non-thermal glow of Sagittarius A, distinct from thermal starlight, a relic of violent processes deep within. Reber's backyard dish had sparked a revolution, his maps inspiring the Cambridge crew to detect the 3 kHz line from hydroxyl in 1963, tracing cold clouds feeding the core, while in Australia, the Molonglo Observatory's East-West Array in 1965 imaged the bulge at 86 MHz, low enough for broad views, but high for detail, showing Sagittarius A as the sky's second brightest radio beacon, after Cassiopeia A supernova echo. By the 1970s, the veil lifted further with higher frequencies, the Very Large Array under construction in New Mexico, promising baselines up to 27 miles. But even then, Sagittarius A star's core eluded full grasp, its radio flux density, measured at 1 Jansky, Jansky's own unit for flux, a nod to the pioneer, holding steady at gigahertz bands, while varying at shorter waves, flares lasting hours, suggesting orbiting hotspots or shocks in an accretion disk, though our black hole's low appetite kept it dim compared to feasting monsters elsewhere. This radio symphony, from Jansky's accidental hiss to arrays harmonizing global data, transformed the hidden heart into a visible vortex, dust no longer tyrant, but transparent to these long waves, revealing a galaxy, not static, but dynamic, arms trailing hydrogen rivers toward the core, where Sagittarius A orchestrated the dance with gravitational might. The whispers grew to roars, each antenna an ear to the cosmos, uncovering not just position, but physics, plasma frequencies, Faraday rotation, twisting polarization, as waves plied magnetic mazes, all painting Sagittarius A as no mere star, but a supermassive enigma, quiet now, but once perhaps a quasar roaring across the young universe. Pioneers like Ruby Payne Scott in Sydney, the first woman in radio astronomy, detected solar bursts in 1945 that honed techniques for galactic sources, or Edward Purcell's 1946 detection of interstellar hydrogen, paving the way for core dynamics, each step building on Jansky's foundation, turning static into science. The veil, once ironclad, frayed thread by thread, radio's gift, allowing us to hear the galaxy's heartbeat, a pulse from Sagittarius that promised revelations beyond imagination. For if waves could unlock this, what other secrets waited in the static, behind the impenetrable curtain of cosmic dust that once made the heart of our Milky Way a tantalizing mystery, a revolution quietly unfolded, not with visible light, but through the warm, ghostly glow of infrared eyes, that pierced the darkness, revealing a crowded, energetic center, bustling with stars and secrets. Imagine standing at the edge of a dense fog bank. Normal light scatters and fades, but if you had special glasses to see in heat instead of brightness, suddenly the hidden shapes emerge, sharp and alive. This is exactly what infrared astronomy accomplished. When scientists realized that to see the galactic core, they had to look beyond the spectrum our eyes were built for. As early as the mid-20th century, ground-based astronomers placed telescopes atop mountains like Mauna Kea in Hawaii and the Chilean Atacama Desert, where thin, dry air allowed faint infrared signals an easier passage, revealing regions completely invisible to traditional optics. The breakthrough was monumental, regions obscured by clouds of dust that blocked visible stars, lit up like neon signs in this new band. Clusters of young hot stars, blazing in infrared and cold clouds, warming up in shadows, flickered into view, transforming darkness into a bustling cityscape. NASA's Spitzer Space Telescope, launched in 2003, brought this revolution into space, soaring above Earth's atmospheric absorption to capture unprecedented infrared images of the galactic center, bathing in the glow of stars, warm dust, and gas swirling around a dense, invisible core. Spitzer's cameras unraveled the crowded stellar neighborhoods with incredible clarity, revealing a cosmic dance where millions of stars orbited an unseen gravitational anchor, while warm dust clouds glowed softly, traced magnetic fields sculpting the region's architecture. Meanwhile, powerful ground facilities, like the European Southern Observatory's Very Large Telescope in Chile, used adaptive optics, systems that corrected atmospheric blurring in real time, to track individual stars as they curved around the galactic center with astonishing speeds, some completing orbits in mere years rather than centuries, providing critical clues to the mass and nature of the hidden beast. One striking revelation was the discovery of stars named S-stars, especially S2, which traced tight elliptical paths at incredible velocity around an invisible point, whose gravitational grip was measured to be about 4 million times the mass of our Sun, compacted into a space smaller than our entire solar system, an unmistakable signature of a supermassive black hole, defying direct observation, yet betraying itself through cosmic choreography. Balloon-borne observatories, like NASA's Stratospheric Terahertz Observatory, soared above most of the atmospheric interference, capturing mid-infrared and sub-millimeter wavelengths to map the cold dust and molecular clouds surrounding the core, painting a picture of a dynamic ecosystem where star formation and black hole feeding intertwined. These molecular clouds, nurseries of new stars, showed how matter cycles through phases heated by stellar winds and activity, obscuring and revealing different layers of the galactic heart. Observations captured episodic flares of infrared light, brief but intense, emanating from close to the black hole, suggesting magnetic turbulence and infalling gas clumps heating to millions of degrees. While the black hole itself swallows light, the environment around it glows brilliantly in infrared, a turbulent furnace at the brink of unimaginable gravity. To understand the galactic center's full complexity, astronomers combined data across the electromagnetic spectrum, but infrared remained king because it could penetrate the thick dust, revealing a galactic core teeming with life and cosmic activity rather than the barren void once imagined. The insight gained reshaped our understanding of galaxy formation and evolution, providing direct evidence that supermassive black holes live symbiotically within dense star clusters, influencing star birth and galactic structure through gravitational and energetic feedback. As the James Webb Space Telescope took over from Spitzer, expected to see even fainter stars and sharper details in the infrared, the story continues to unfold, promising discoveries that will challenge and expand our cosmic perspective, all thanks to the special infrared eyes that can peer through the dust and bring light to the universe's darkest secrets. Imagine the moment when astronomers, peering through infrared lenses that finally cut through the dusty haze. Spotted stars hurtling around an invisible point like daredevils in a gravitational circus, their paths curving so sharply and swiftly that no ordinary force could explain it, whispering the undeniable truth of a supermassive beast lurking at our galaxy's core. A black hole, not just massive, but colossal, weighing 4 million times the sun's heft, yet squeezed into a space tinier than Mercury's orbit. This wasn't some distant quasar or theoretical fancy. It was right here, in the Milky Way's heart, Sagittarius A star, its presence etched in the frantic dance of those Say stars, especially the bold S2, which zipped along an elliptical track, completing a full loop in just 16 years, reaching speeds over 3,000 kilometers per second at its closest approach, close enough to graze the beast's influence, where gravity warps reality itself. Teams led by Reinhard Genzel at the Max Planck Institute and Andrea Ghez at the University of California, Los Angeles, had been watching for decades, their telescopes on Hawaii's volcanoes and Chile's mountaintops, armed with adaptive optics that ironed out the atmosphere's twinkling distortions, allowing them to track these stellar speedsters with pinpoint accuracy, measuring positions to within 1,000th of an arc-second, the angular width of a human hair seen from a mile away. By the early 2000s, the orbits closed the case. SIF-2's path, observed from 1995 onward, revealed an enclosed mass of 4.1 million solar masses, confined to a radius of less than 1/10 of a light year, far too dense for a star cluster, which would scatter under its own weight, or a neutron starball, too small to hold such pull. Only a black hole fit, its event horizon a point of no return, where light bends and time dilates, pulling stars into elliptical frenzy without emitting its own glow. The evidence stacked like cosmic dominoes. Other S-stars, like S16 and S19, followed similar arcs, all orbiting the same dark anchor, their velocities peaking near the center, in perfect agreement with general relativity's predictions, where space-time curves so intensely that orbits precess, shifting like a wobbling top, a subtle twist Newton's laws couldn't account for, observed in S2's closest pass in 2002, when it slingshotted just 17 light hours from the hole, its light redshifted by gravity's grip. This wasn't indirect hunch, it was direct proof, earning Genzel and Ghez the Nobel Prize in Physics in 2020, shared with Roger Penrose for theoretical groundwork, confirming that supermassive black holes aren't rarities but rule the roost in galactic cores. Sagittarius, a star, a quiet example compared to the blazing active ones, powering quasars across the cosmos. But why quiet? Unlike those feasting giants spewing jets of plasma and X-rays from accretion disks of swirling gas heated to millions of degrees, our beast sips sparingly, its low luminosity, about 1/10 millionth of what it could devour, suggesting a sparse diet of stray gas clouds and occasional stars. Yet even in dormancy, it flares briefly, infrared and X-ray bursts every few hours as magnetic loops snap or clumps of matter tumble in, lighting up the inner 10 light minutes like fleeting fireworks. Types of black holes paint the bigger picture. Stellar mass ones, born from collapsed giants, 10 to 100 times the sun's mass, lurk by the millions in the galaxy, detectable only when they steal from companions, glowing in X-rays like Cygnus X1, but too puny at 5 to 20 solar masses to anchor a galaxy. Intermediate ones, hundreds to thousands solar masses, elusive bridges, perhaps forged in dense clusters or mergers, candidates like the one in Omega Centauri, hinting at seeds for giants, yet rare sightings leave their role murky. Primordial black holes, theorized relics from the Big Bang's density ripples, could range from asteroid size to stellar, invisible wanderers, maybe explaining dark matter, but unproven. While ultramassive behemoths over 10 billion solar masses dwarf ours in giants like Phoenix A, their growth the puzzle of relentless feeding in the early universe. Sagittarius A star sits squarely supermassive, 4 million solar masses, making it middling, dwarfed by Messier, 87 6.5 billion, yet vast enough to shape the bulge's 400 billion stars. Its Schwarzschild radius, the event horizon's edge, spanning just 12 million kilometers, about the sun's diameter, a boundary where escape velocity hits light speed, trapping photons in eternal fall. This proof reshaped cosmology. Every major galaxy harbors one, from spirals like ours to ellipticals, their masses correlating tightly with bulge stellar velocity, dispersions via the M-sigma relation, suggesting coevolution, where black holes regulate star formation by blasting outflows that quench gas clouds, or galaxies feed holes through bars, funneling matter inward. In our case, the holes spin, inferred at 90% light speed from X-ray spectra and recent Event Horizon Telescope data, hints at a past merger, perhaps with a swallowed satellite galaxy's core, tilting its axis 40 degrees off the galactic plane. A violent history, echoing the Milky Way's cannibalistic youth. Gas dynamics sealed the deal too. Ionized clouds near the core, tracked via forbidden emission lines and spectra, whirl at thousands of kilometers per second, their Keplerian decline with distance, screaming concentrated mass, while microlensing events, stars briefly magnifying background light, revealed a crowded cusp of faint dwarfs orbiting the hole, adding to the gravitational tally. No alternatives held water. A dense ball of dark matter would disperse. Exotic particles couldn't mimic the tight orbits, and even wormholes, or naked singularities, violated observations. The black hole, with its singularity cloaked by the horizon, was the elegant fit, predicted by Einstein's equations, where mass curves space-time into inescapable wells. Today, ongoing watches with the Keck and Very Large Telescopes catch CES-2's every swing, refining mass to 4.3 million solar masses, plus or minus a few percent, while Chandra X-ray Observatory flares probe the inner flow, showing a thin disk starved by winds from the bulge's hot stars. This beast isn't just proven, it's a living lab, testing relativity near the edge, where frame-dragging twists, light paths, and quantum effects might peek from the horizon's quantum foam. Future gravitational wave detectors like LISA could catch echoes of its mergers, rippling space-time from billion-year-old collisions. But for now, the stellar dance proves it beyond doubt. A supermassive guardian, silent yet supreme, anchoring our galactic whirl and inviting us to wonder what other beasts prowl the universe's depths. Jabul Chu, the Odyssey, to unveil the first direct image of Sagittarius A star, the enigmatic supermassive black hole commanding the gravitational throne at the very core of our Milky Way galaxy, stands as one of the most audacious triumphs in the annals of astronomical exploration, a narrative woven from threads of relentless curiosity, cutting-edge innovation, and international collaboration that spanned over a decade, transforming what was once dismissed as an impossible dream into a groundbreaking reality, unveiled to the world on May 12th of 2022. This monumental achievement was spearheaded by the Event Horizon Telescope collaboration, a global alliance of over 300 scientists from institutions across more than 60 countries, who orchestrated a symphony of synchronized observations using 8 premier radio observatories positioned strategically around the planet. From the frigid isolation of the South Pole Telescope in Antarctica, where temperatures plunge to -80 degrees Fahrenheit and winds howl like cosmic banshees, to the sun-baked Atacama Large Millimeter Submillimeter Array in Chile's high desert, spanning 66 antennas that together form the most sensitive radio eye on Earth, and extending to the volcanic heights of Mauna Kea in Hawaii with its submillimeter array and James Clerk Maxwell Telescope, the sun-drenched Large Millimeter Telescope in Mexico's Sierra Negra, the IRAM 30-meter dish in Spain's Sierra Nevada, the Greenland telescope perched on ice sheets, and the crucial Atacama Pathfinder experiment in Chile, all linked in a virtual behemoth that effectively turned our entire planet into a telescope the size of Earth itself, with a baseline stretching nearly 8,000 miles from pole to pole. The genesis of this endeavor traces back to the early 2000s, when visionaries like Shepard Doleman at the Harvard-Smithsonian Center for Astrophysics began pondering how to peer into the abyss of black holes, inspired by theoretical predictions from Einstein's general theory of relativity that a black hole's event horizon, the point of no return, where gravity's grip becomes so absolute that even light cannot escape, would cast a distinctive shadow against the luminous backdrop of superheated plasma, swirling in its accretion disk, a shadow roughly twice the diameter of the event horizon itself, due to the lensing effect of space-time curvature, bending photons into a photon ring that encircles the darkness like a cosmic halo. For Sagittarius A, this shadow was calculated to span about 50 microarc seconds across, an angular size so minuscule it equates to spotting a donut on the surface of the moon from Earth, or distinguishing the width of a human hair from a distance of 2,000 miles, demanding a resolution that no single telescope could provide. Hence the birth of very long baseline interferometry at millimeter wavelengths, a technique pioneered in the 1960s, but refined for this purpose to capture radio waves at 1.3 millimeters, short enough to resolve fine details, yet long enough to penetrate the interstellar dust, veiling the galactic center. The campaign kicked off in earnest in April of 2017, when under clear skies and precise timing, the telescopes recorded data for hours on end, capturing the faint radio emissions from gas orbiting the black hole at speeds approaching 100,000 kilometers per second, heated to billions of degrees and glowing in synchrotron radiation as electrons spiral in tangled magnetic fields. But the variability of Sagittarius A threw immediate curveballs. Unlike the stately, stable accretion flow around the much larger M87 star black hole imaged in 2019, which is 6,500,000,000 solar masses and orbits material over days, Sagittarius A star's 4 million solar masses meant its inner disk churned with changes every few minutes, brightness fluctuating by up to a factor of 10 as hotspots formed and faded, interstellar scattering from electrons in the galactic plane, further blurring the signal like looking through frosted glass, and Earth's atmosphere added its own turbulence, refracting waves unpredictably, all compounding to make the data a chaotic puzzle requiring heroic computational feats. The raw haul was staggering, 5 petabytes of information, equivalent to streaming all Netflix content for over 100 years, without pause, too voluminous for internet transfer. So hard drives were flown commercially to processing hubs, the Haystack Observatory in Massachusetts, and the Max Planck Institute in Bonn, where supercomputers crunched numbers using correlation engines to align signals delayed by thousands of miles. Atomic clocks synced to within a trillionth of a second, ensuring phase coherence. And then the real magic began with imaging algorithms, like the clean method, originally developed by Jan Hogbaum in 1974 for radiosynthesis, evolved into advanced tools such as the regularized maximum likelihood and the dynamical imaging that accounted for time variability by treating the source as a movie rather than a static picture, iterating through thousands of models to reconstruct the ring while suppressing noise and artifacts. 5 grueling years of analysis followed, with teams working in parallel across continents, debating every pixel in virtual meetings that bridge time zones from Tokyo to Santiago, cross-validating results against simulations from general relativistic magneto-hydrodynamic codes that modeled plasma flows around spinning black holes, predicting the lopsided ring brighter on the approaching side due to relativistic beaming and Doppler shift, where light from gas hurtling toward us at 90%. The speed of light gets blue shifted and amplified, while the receding limb dims, a telltale sign of the black hole's rotation, estimated at about 0.5 to 0.9 times light speed. When the image finally emerged, it was a revelation. A fuzzy yet unmistakable asymmetric ring of orange fire encircling a pitch-black void, the shadow's diameter aligning precisely with predictions for a 4 million solar mass. Kerr black hole validating Einstein's equations to within 10%, and stirring global headlines from the New York Times to BBC broadcasts, with President Joe Biden calling it a profound accomplishment that underscored humanity's place in the cosmos. But the story delved deeper. Polarization data, released in March of 2024, mapped the magnetic fields threading the ring, showing spiral patterns consistent with strong, ordered fields that could propel plasma outflows, hinting at why Sagittarius A remains quiescent today, compared to its active quasar-like past, billions of years ago, when it likely feasted voraciously, sculpting the galaxy's bulge. This imaging saga, intertwined with decades of precursor work. In the 1990s, radio interferometers, like the Very Large Array in New Mexico, had resolved Sagittarius A to within 100 microarc seconds, revealing its compact core variable on timescales of hours, while infrared observations from the Keck telescope tracked the Chess-2 star's orbit, its closest approach in 2018, showing gravitational redshift. As predicted by relativity, light stretched to redder wavelengths by the hole's immense pull, confirming the mass to 4.3 million solar masses, plus or minus 0.4%. The EHT's triumph built on this foundation, but challenges abounded. Calibrating for atmospheric water vapor, absorption at millimeter waves, required precise weather monitoring, plagued with observations aborted on cloudy nights. And the South Pole site's remoteness meant data waited months for extraction via ice runway flights. Yet each obstacle forged resilience, culminating in not just an image, but a dataset ripe for mining, revealing flaring events where X-ray bursts from Chandra align with radio brightenings, suggesting asteroid disruptions or magnetic reconnection events, injecting energy near the horizon. Culturally, the image ignited wonder. Featured in art, exhibits from the Smithsonian to virtual reality simulations, allowing armchair explorers to fly toward the ring, while scientifically, it opened floodgates. Comparisons to M87 star showed Sagittarius A star's smaller shadow scales, with mass as expected, but its faster variability probes, accretion physics, in a low luminosity regime, where Eddington limits, the maximum brightness before radiation pressure halts in fall, are barely grazed, unlike quasars radiating at thousands of times that. Future horizons gleam brighter. The EHT's expansion to 10 stations by 2025, including the Africa Millimeter Telescope and East Asia's Nobeyama, promises sub-micro-arcosecond resolution, enabling movies of orbiting hotspots, while the NGVLA in the United States and the African VLBI network will boost sensitivity 100-fold, potentially detecting the photon ring substructure or even shadows from intermediate mass black holes nearby. Space-based additions, like the proposed Black Hole Explorer, could baseline across Earth's orbit, tripling resolution, and synergies with James Webb Space Telescope's mid-infrared views will correlate dust-obscured features with radio emissions, unraveling how Sagittarius S star influences star formation in the central molecular zone, a cauldron of 500 solar masses per cubic parsec, where clouds like the Brick spawn massive stars, despite the hole's sterilizing radiation. This impossible image, born from human persistence against cosmic odds, not only demystifies our galactic heart, but redefines black holes from mathematical curiosities to observable entities, challenging us to ponder their role in the universe's grand tapestry. From seeding galaxy formation in the Big Bang's aftermath to merging in gravitational wave symphonies detected by LIGO, echoes of which might one day ripple from Sagittarius, a star's own collisions, perhaps with a swallowed dwarf galaxy's core tilting its spin axis 30 degrees off the galactic plane. In classrooms worldwide, it sparks young minds, much like Galileo's telescope did 4 centuries ago, reminding us that the stars, once points of light, now reveal monsters within, inviting endless questions. What lies beyond the shadow? Where quantum gravity meets classical curves, or how this quiet beast, dormant for 200 years per NASA's INSPE findings of its recent awakening from debris feasts, might roar again in 4 billion years, when Andromeda collides, merging black holes in a spectacle of light and waves. Thus, the impossible becomes icon, a testament to collaboration transcending borders, a beacon illuminating the invisible, and a portal to infinities, yet unexplored. Say whatje? Sagittarius, a star, the supermassive black hole at the core of our Milky Way galaxy, holds a gravitational influence so profound that it choreographs the orbits of stars thousands of light years away, anchoring the sprawling spiral arms and swirling masses of interstellar gas and dust in an intricate cosmic dance. At over 4 million times the mass of our Sun, compressed into a region smaller than our solar system, its impact extends far beyond its immediate neighborhood, shaping star formation, galactic evolution, and even the conditions for life within the Milky Way. The black hole's gravitational pull governs stars known as S-stars that orbit its invisible maw at breathtaking speeds, with the fastest swinging around it in just over a decade, tracing paths that confirm not just the mass, but also the shape of the gravitational well, tightly fitting predictions from Einstein's general relativity. This precise celestial clockwork is the most direct evidence of a supermassive black hole's presence and power. But Sagittarius A's influence stretches further, sending out energetic feedback in the form of high-energy radiation and jets that carve vast bubbles of hot gas and X-rays far above and below the galactic plane. These astronomical phenomena, known as the Fermi bubbles, span tens of thousands of light years, likely inflated by past outbursts when the black hole consumed greater amounts of material, releasing energy that heated and pushed away surrounding gas, regulating the rate at which new stars could form in the central bulge. This interplay between a black hole's feeding and a galaxy's growth underscores a fundamental cosmic alliance where supermassive black holes act as cosmic governors, controlling their galactic environment, keeping the delicate balance between creation and destruction. Astronomical observations have revealed that Sagittarius, a star, remains relatively dormant in the current epoch, feeding only sporadically on stray gas clouds or occasionally disrupted stars, leading to intermittent flares detected across the electromagnetic spectrum. These flares, some emitting bursts of X-rays and infrared light, illuminate the complex magnetic and gravitational interactions near the event horizon, where matter accelerates and heats to millions of degrees before crossing the point of no return. The quiescent state of Sagittarius, the star, contrasts with the active black holes seen in other galaxies, particularly distant quasars emitting prodigious jets of energy visible across the universe. It is believed that our galactic center has undergone periods of heightened activity in the past, and may do so again in the future. Looking ahead, the future of Sagittarius, a star, is intertwined with the destiny of the Milky Way galaxy itself, as it moves inexorably toward a colossal collision with the neighboring Andromeda galaxy. This galactic merger, expected to occur in roughly 4 billion years, will lead to a dramatic reconfiguration of both galaxies, with their supermassive black holes spiraling together in a gravitational embrace that ultimately melds them into a single, even more massive entity. Such black hole mergers produce gravitational waves, ripples in the fabric of space-time that ripple through the cosmos. Future space-based gravitational wave observatories, planned for the next few decades, may detect echoes from such mergers, offering unprecedented insight into these violent cosmic dances and the growth of black holes. Closer to our own time, studies using observatories, such as NASA's 9CPE and Chandra X-ray Observatory, have detected recent awakening phases of Sagittarius A. Evidence suggests that just 200 years ago, the black hole underwent an energetic flare, possibly from the tidal disruption of a passing comet or asteroid, unleashing X-ray emissions millions of times stronger than ambient levels. Such awakening phases are likely to recur sporadically as the black hole continues to interact with the chaotic stellar environment surrounding it. The galactic bar, a large elongated distribution of stars and gas crossing the Milky Way's disk, periodically funnels material toward the central region, potentially triggering new feeding episodes and energetic outbursts that could reshape the central molecular zone, a dense region rich in molecular clouds where star formation is ongoing. Sagittarius, a star's spin, measured indirectly through high-resolution spectral studies and supported by recent artificial intelligence analyses, is estimated to be approximately 60 to 90% of the theoretical maximum allowed by general relativity. This rapid spin influences not only the dynamics of the accretion disk, but also the production of relativistic jets and the dragging of space-time itself, known as frame dragging. These effects manifest as distortions in orbiting material, timing shifts in flares, and the alignment of magnetic fields near the horizon, all of which astronomers continue to study to unravel the black hole's complex behavior. The black hole also indirectly shapes the larger-scale structure of our galaxy, influencing star formation rates and distributing heavy elements vital for planet formation and life. Its past outbursts have likely played a role in enriching the interstellar medium, with elements forged in the cores of stars that once orbited too close and were torn apart. Thus, Sagittarius A* is as much a creator as a destroyer, a primal force that both tempers and nurtures the galactic ecosystem. Humanity's gaze into this dark heart has transformed from theoretical supposition to direct observation and dynamic modeling, enabled by remarkable advances in technology, ranging from adaptive optics, telescopes, tracking stellar orbits with exquisite precision, to the Earth-spanning Event Horizon Telescope, rendering the black hole's silhouette for the first time. Continuous monitoring promises to unlock new mysteries, capturing real-time variations in accretion flows and magnetic field interactions, eventually presenting movies of the complex interplay of matter and energy just outside the event horizon. The future holds the promise of even greater insights as next-generation telescopes launch and arrays expand, further unveiling the secrets of the supermassive black hole that governs our cosmic neighborhood. In this grand cosmic saga, Sagittarius A* stands as the embodiment of both awe-inspiring power and subtle influence, a remnant of the universe's earliest epochs, and a dynamic actor shaping galactic futures. Its echoes of influence ripple through time and space, marking the Milky Way's past, present, and future, inviting us to contemplate our place amidst the celestial tides, driven by this silent yet formidable galactic monarch. From the dusty veil that once shrouded the heart of our Milky Way to the groundbreaking image that finally pierced the darkness, the story of Sagittarius A* stands as a testament to humanity's unyielding quest to unravel the universe's deepest mysteries, a journey that began with ancient stargazers peering through the haze of the night sky, mistaking the faint milky band for a river of gods or a path to the afterlife, only to discover in the 20th century that it concealed a colossal force at its core, a supermassive black hole weighing 4 million times the mass of our Sun, yet squeezed into a space smaller than the orbit of Mercury, its gravitational whisper shaping the orbits of billions of stars across 26,000 light-years, including our own solar system, which circles this invisible monarch every 225 million years at a steady clip of 220 kilometers per second. This epic tale unfolded layer by layer, starting with the hidden heart, where interstellar dust, those microscopic grains of carbon, ice, and silicates, forged in the furnaces of ancient stars, blocked visible light like a cosmic fog, frustrating early astronomers, from William Herschel in the 18th century, who tallied stars with homemade telescopes and imagined the galaxy as a grindstone with us at the center, to Harlow Shapley in the 1910s, who used globular clusters to shift our position to the outskirts, but still couldn't pierce the bulge's obscurity, a swollen sphere of 400 billion stars crammed into a space, 10,000 light-years across, denser than the outer arms by a factor of 1,000, where collisions and gravitational tugs birthed a frenzy of activity hidden from our gaze. It took the accidental genius of Karl Jansky in the early 1930s, tinkering with radio static at Bell Labs to clear transatlantic phone lines, to hear the first whispers from the stars, his merry-go-round antenna spinning under New Jersey skies and capturing a persistent hiss every sidereal day, 23 hours and 56 minutes, strongest towards Sagittarius, birthing radio astronomy and revealing the galactic core as a blazing radio beacon. Sagittarius A, a compact hotspot amid diffuse glows, slipping past dust that devoured optics but yielded to long wavelengths, paving the way for Grote Reber's backyard dish in 1937 to map the radio sky and confirm the Milky Way's spiral arms, coiling around this enigmatic point. Infrared eyes then joined the fray in the mid-20th century. Telescopes on dry mountaintops like Mauna Kea and the Atacama Desert, capturing heat glows from warm dust and hot young stars. NASA's Spitzer Space Telescope, launched in 2003, soaring above atmospheric water vapor to unveil the central molecular zone, a cauldron of gas clouds and stellar nurseries, where the black holes pull compressed matter into diamond-hard knots, triggering star birth even as it sterilized the innermost parsec. And adaptive optics on the Very Large Telescope in Keck Observatory tracked the S-stars like the speedy S2 zipping in a 16-year ellipse at 3,000 kilometers per second, their paths curving so tightly around an unseen anchor that only a black hole could explain the enclosed 4 million solar masses within a light-year radius, earning Reinhard Genzel and Andrea Ghez the Nobel Prize in 2020 for proving this supermassive beast beyond doubt. Its event horizon, a mere 12 million kilometers across, where escape velocity matches light speed and time dilates into eternity. The impossible image crowned this saga in 2022, when the Event Horizon Telescope, a planet-spanning array of 8 radio dishes from Antarctica's ice to Hawaii's peaks, linked via atomic clocks, very long baseline interferometry, to form an Earth-sized eye, capturing 1.3 millimeter waves bent by gravity into a 50 micro-arcsecond ring of blazing plasma, encircling a dark shadow, the first direct portrait of Sagittarius A star, reconstructed from 5 petabytes of data, hauled by plane to supercomputers, battling the hole's rapid variability as hotspots orbited in minutes, interstellar scattering, blurring the view like cosmic heat haze, yet emerging asymmetric and lopsided, brighter on the approaching side from relativistic beaming, validating Einstein's general relativity to within 10%, and mapping spiral magnetic fields that thread the accretion disk, hinting at faint jets and a spin 90% of maximum, a Kerr black hole twisting spacetime with frame dragging. These echoes of influence ripple far beyond the core. Sagittarius A star, not a passive void, but a galactic architect, its gravity anchoring the rotation curve that flatlines at constant speeds thanks to the dark matter halo, while past outbursts 2 million years ago inflated the Fermi bubbles, twin gamma-ray lobes, 50,000 light-years tall, carved by winds equivalent to 100 supernovas, sweeping gas from the bulge and quenching star formation, regulating the stellar census like a thermostat, and enriching the interstellar medium with heavy elements from tidally shredded stars, the very iron in our blood, and carbon in our cells, forged in those disruptions, seeding the chemistry that birthed Earth 4.5 billion years ago. Even in quiescence, it flares sporadically. X-ray bursts every few hours from NASA's Chandra, ENICP, detecting a 200-year awakening in the 1800s, perhaps from a comet's plunge or magnetic reconnection. Luminosity spiking to 1,000,000 times normal, while James Webb's mid-infrared gaze in 2025 caught rapid-fire twinkles lasting seconds, hotspots whipping around the horizon every 20 minutes, and gravitational microlensing hints at thousands of stellar mass black holes lurking within 3 light-years, remnants of a crowded youth that could merge with the giant over eons, chirping low-frequency waves for LASA in the 2030s to hear. Yet this quiet phase belies a future fury scripted in the stars. The Milky Way's bar, that skewer of stars funneling gas inward every 100 million years, might awaken the beast into quasar mode, devouring at its Eddington limit and blasting outflows that scorch the central zone, while in 4 billion years, Andromeda's approach at 400 kilometers per second heralds the Milky-Way merger, stars sailing past unscathed. But the two holes, ours 4 million solar masses, theirs 30 million, spiraling together via dynamical friction, their disks grinding into relativistic fury, jets plowing gas and ionizing clouds across 100,000 light-years, the final plunge unleashing gravitational waves 1,000 times. LIGO's neutron star chirps, warping space-time, and perhaps perturbing our descendants' worlds with tidal tides or radiation storms. This saga of Sagittarius, a star transcends science, igniting wonder in every heart that tilts skyward, from Babylonian priests, charting constellations to YouTube creators, scripting cosmic tales for eager viewers, reminding us that we are stardust orbiting a monster, fragile specks in a galaxy of 400 billion lights, yet bold enough to image the unseeable. Our telescope's extensions of curiosity that peeled back veils of dust and distance, radio whispers, and infrared glows, converging on a shadow that proved Einstein right, while teasing quantum secrets at the horizon's edge, where Hawking radiation might flicker unobserved, and singularities challenge infinity. As we stand on this precipice, the black hole beckons further exploration. Next-generation arrays like the NGVLA, promising movies of infalling matter, space-based baselines, tripling resolution to film the photon ring's substructure, and synergies with Roman's wide-field surveys, spotting wandering holes or primordial relics that could explain dark matter, all while simulations from Illustrist NG paint hierarchical growth from stellar seeds in the Big Bang's chaos, mergers building behemoths that co-evolve with galaxies via the M-sigma relation, black hole mass tying to stellar velocities in a cosmic handshake. In classrooms and observatories, this story sparks the next generation, much like Galileo's moon's shattered geocentrism, now shattering isolation to reveal our galactic family, where Sagittarius A, star isn't apocalypse, but evolution's engine, clearing paths for stars like our sun to ignite in the arms it stabilizes. Its future collision, not end, but rebirth, forging a new elliptical giant that drifts through the local group, perhaps birthing exotic worlds or quiet voids. Thus, the conclusion isn't closure but crescendo, an invitation to dream bigger, to launch probes toward the core or colonize arms beyond its reach, pondering if life elsewhere orbits similar beasts, their flares painting auroras on alien skies, or jets seeding habitable zones with organics. For in Sagittarius, a star's silent roar, we glimpse the universe's poetry, gravity's embrace, weaving destruction into creation, darkness birthing light, and humanity, humble observers, etching our chapter in the star's eternal narrative, forever hooked on the cosmic hook that pulls us toward the infinite. Unseeable.